Okay, today we're going to talk about the Trapezoid rule and Simpsons rule, uh, which are formulas that we can use to approximate the value of a definite integral that can't be integrated. If we haven't mentioned this before, it's worth pointing out, unlike derivatives, they're pretty much, once you learned all your formulas, there pretty much wasn't any function you couldn't take the derivative of. You just had to use the correct formula. But there's tons of functions that have no antiderivative. A good example, like the integral of e to the x squared dx, or the integral of 1 over natural log of x. These are integrals that it's been proven there's no way to find an antiderivative for that, which means you can't really evaluate these integrals using the fundamental theorem of calculus. Nevertheless, these functions, y equals e to the x squared, there's a graph associated with that. And if you were integrating from 0 to 2, it would be the equivalent to finding the area under that graph. So just because we can't integrate it doesn't mean there isn't area that can't be found. But the best we're going to be able to do is to just approximate the value of the definite integral. A little bit what we've done earlier in the quarter when we were doing building the Riemann sum idea using left and right hand endpoints and midpoints with rectangles to approximate an integral. So it is something we have talked about, only these are two different techniques. The real use for trapezoid rule and Simpsons rule are for integrals like this that can't be done, but just so we can apply both of these rules and have a sense of how accurate we are, let's use, in this case, we're going to approximate the integral of 1 over x dx using from 1 to 3 using the trapezoid rule with n equals 4. Now, of course, there's no real reason to approximate it because we can actually evaluate that integral using the fundamental theorem of calculus. So, and we're going to do that because then we'll know what to compare our answer to. So the antiderivative is ln of x, evaluated from 3 to 1 gives me ln of 3 minus ln of 1. ln of 1 is 0. So the correct exact answer is ln of 3, which is approximately 1.0986. Okay. To approximate this with the trapezoid rule, think about the graph. And we're going to, just like with Riemann sums, if we're using n equals 4, we're going to partition the interval from 1 to 3 with 4 equal subintervals. We still talk about delta x being b minus a over n. So 3 minus 1 divided by 4 gives me delta x as 1/2. So then I can find my interior points. And as the name implies, we're going to approximate this using trapezoids, which, if you think about it, makes a lot of sense. Previously, what we were doing with these numbers is we were either choosing the left-hand endpoint and making a rectangle that clearly way overestimates the area under the curve, or using right-hand endpoints where you make a rectangle where you very much underestimate the value of the integral because you're going horizontally, right? So the trapezoid rule makes a lot of sense if you have a curved graph because you're going to just connect this point and this point with a straight line. And you can see there's very little error between the curve and the trapezoid. Of course, I haven't drawn this to scale, but the error is much smaller than if you used rectangles. The formula is based on the area of a trapezoid, which from geometry, usually you talked about a trapezoid having 2 bases and a height, a vertical height, that was a right angle here. And the formula was 1/2 b1 plus b2. So you're basically averaging the 2 bases and then multiplying by the height. So applying that here, of course, our trapezoids are standing up vertically here. So the height of our trapezoid is the equivalent to delta x. And the b1 and b2, the bases, are just the value of my function at these numbers. So my first trapezoid, using the formula, would give me 1/2 f of 1 plus f of 3 halves times delta x, which is my height. For the second trapezoid, it would be 1/2 f of 3 halves plus f of 2 times delta x, and so forth. So I showed it this way because hopefully you can see, well, to make the process simpler, every term has a delta x and a 1/2, so we can factor that out. And what are we left with is we're going to have f of 1. We're going to get an f of 3 halves there and an f of 3 halves there. Why? Because f of 3 halves, this counts as a base for two trapezoids. So does f of 2. So does f of 5 halves. So the interior x values get counted twice. And that's because they are walls, so to speak, of two trapezoids. And this is sort of a good model, right? Of course, the numbers will change on different problems, but I'm not into, probably noticed, formulas. This is basically a model, right? You're going to do 1/2 delta x, f of your first number plus 2f of all the interior values, and then at the end, the last number is going to get counted once. So for our particular problem, if you run the numbers, we get about 1.1167. So the exact error, I put almost because remember we had to approximate ln of 3 as 1.0986. We had to cut off the decimal somewhere, but close enough, right? To 4 decimal places, my exact error, I would just take the difference between the exact answer and this answer, the absolute value of that, because I don't really care if I'm positive or if I'm above or below. And I get 0.0181. Very, very good approximation. Right? Only off by less than 2/100ths. Now, the question, of course, is what if we were not able, I introduced this by saying the real use of the trapezoid rule and Simpson's rule was for integrals that could not be worked out by hand with the fundamental theorem of calculus, in which case, how am I going to know what my error is? So we have what we call an error bound formula that, okay, the derivation of this is very complicated. Don't worry about it. The main thing is you just need to know how to use it. And it's a bound. All this is saying is the error in using the trapezoid rule, the absolute value, will be less than or equal to b minus a cubed over 12n squared times the maximum value of the absolute value of your second derivative of x, where x is any number between a and b, the limits of your integral. So let's see how that works here. If I was using this error estimation formula, let me slide this back down a little bit, to put an error, an upper bound on the error in approximating this integral with 4 trapezoids. The trickiest part of this formula is this part here where you have to find the maximum value of your second derivative on the interval from a to b. So you start with 1 over x, take 2 derivatives, and then the idea is, remember your a and b were 1 and 3. So if you got to plug in any number between 1 and 3, including 1 and 3, into this function, 2 over x cubed, what would be your biggest value you could get out of that? And the thinking here would be, the only place I get to plug in a number is the denominator, and fractions are big when denominators are small. So in this case, the number that's going to maximize my second derivative is going to be 1. Okay. And that gives me 2 over 1 cubed, which is 2. And then if I finish this off, the error in my trapezoid rule then would be 3 minus 1 cubed over 12 times 4 squared times this 2 that I got here, which comes out to be 1/12, which is 0.0833. So to be clear, what is this saying? This isn't saying that is the error. It's saying my actual error, if I use the trapezoid rule with n equals 4, cannot be any bigger than 0.0833. And we can confirm that this was true because we actually were able to compute the exact error. 0.0181, and it was less than 0.0833. So notice this isn't even really necessarily that close. It's just an upper bound. My error cannot be any worse than that, and it definitely was not any worse than 0.0833. There's another integral estimation tool called Simpsons Rule. And I want to give you a little background on what this is about. Simpsons Rule involves parabolas. And it's a pretty interesting idea that you can find the exact area under a parabola using a formula that doesn't involve calculus. So let's practice this just to see how it works. I'm going to find the area under f of x equals x squared plus x plus 1 on the interval from 0 to 4. So how this works, you split the interval 0 to 4 into equally. So you're going to find the midpoint, which is 2, which means I have a delta x of 2. And the way it works is, according to Simpson's rule, the exact area under this parabola is going to be the delta x, the 2 divided by 3, that's always true. And then you're going to evaluate f of the left endpoint plus 4 times f of the midpoint, and then 1 f of the endpoint, the right endpoint. So I get f of 0 is 1, f of 2, if you plug that in, is 7, 4 times 7, and then f of 4 was 21. And you work that all out, and you get an answer of 100 over 3, which, just to prove that is actually the exact error. This is not an approximation. I'm sorry, the exact answer. If you work this out with calculus, you get the same answer. So we can use this idea to approximate areas under graphs even if they are not parabolas. So let's try it on our integral we've been working on. So this same integral from 1 to 3 of 1 over x dx with Simpson's rule, n equals 4. So you would still divide this into 4 subintervals. And the way Simpson's rule works, as we saw, is you need to take 3 points. So we're going to use 1, 3/2, and 2. And it's essentially using those 3 points to model a parabola, which we know will give us, Simpson's rule will give us the exact area under that parabola. And then it's going to take the next 2 subintervals, or 3 points, model a parabola that passes through those 3 points, and then find the area under that. So one thing to notice here is that it takes 2 subintervals to get these 3 points, and then another 2 subintervals to get these 3 points. So when you use Simpson's rule, I'm going to slide this up here, n has to be even. You can't use Simpson's rule with n equals an odd number like 5 or 7. It has to be 4 or 6 or 8, because you need 2 subintervals to get 3 points for your parabola each time. Okay, so using Simpson's rule, the value of that integral is approximately delta x over 3, f of 1, 4 f of 3/2 plus f of 2. But then notice for my next parabola, I need to use the f of 2, 4 f of 5/2 plus 1 f of 3. So the f of 2 is going to get counted twice because it's part of 2 parabolas. And so a general formula for Simpson's rule, again, this is using specific numbers, but it's a good model. Delta x over 3, that part is always true. F of the first number plus 4 f of the next number plus 2 f of the next number, because that's going to be like a transition between 2 parabolas, and then 4 f of 5/2, and when you get to the end, it'll just be counted once. Working that out with our numbers, you can check the fractions, plugging those in, I get 1.1000. Now remember, we actually computed this exact value of this integral to be 1.0986. So if I get my exact error, it's really, really accurate, isn't it? And it makes sense. Think about the graph of 1 over x is a curved graph, and you're modeling a curved graph with a parabola, which is also a curve, right? So it makes sense that it should be better. Very, very accurate with only n equals 4. Now, again, we were only able to determine this because we knew the exact value of the integral. So what if we weren't able to do that? Just like the trapezoid rule, there is an error estimation formula for Simpsons rule, which is and this one's similar. Error using Simpsons rule will be less than b minus a, this time to the 5th, divided by 180 n to the 4th, times the maximum value of your 4th derivative. Remember, trapezoid rule, you only had to use the 2nd derivative, where x is any number between a and b. So if I was to use this, now I need to get to my 4th derivative for this function. So here I'm just taking derivatives to try to put a bound on my 4th derivative. Got to slide this up, which is 24x to the negative 5th, or 24 over x to the 5th. Same idea as trapezoid rule though. On the interval from 1 to 3, if I could pick any number for x between 1 and 3, including 1 and 3, and plug it in for x, which is in the denominator, and I want to make this as big as possible, then I want to choose once again the smallest number, which is 1, to give me 24. And then if I plug that into my formula with my a and b and n being 4, I get a maximum error of 0.0167. And again, this checks out because the actual error, 0.0014, was much less than this maximum possible error. It's just putting a bound. Now, one thing you can do with this error bound formula, what if we were estimating this integral and that was not good enough? What if we wanted it to be even more accurate than 0.0 either of these? Okay, what if we wanted to use Simpsons rule, SR, shorthand, and we wanted to estimate this integral so that it was accurate to within 1 over 10,000, really accurate. Of course, just like with rectangles, when you're using the Riemann sum, the bigger n gets, the more accurate you will approximate that integral. So the question would be, what should n be? How many subintervals do I need to estimate that integral to within 1 over 10,000? So you can use that error bound formula. We already put a bound for the 4th derivative. This time we're going to try to solve for n. Set this less than 1 over 10,000. And if you do the algebra, n comes out to be greater than about 14.37. 2 issues. Number one, remember, n is the number of subintervals. It has to be a whole number. You can't have 14.37 subintervals. And also remember that this is the bare minimum number value for n that makes this true. So you can't go down to 14 or you're not going to be accurate to within 1 over 10,000. So you're going to round up. And also remember, for Simpsons rule, n has to be even, so you can't even round up to 15 because you can't use 15 subintervals for Simpsons rule, so you'd have to go all the way up to 16. All right, let's try this now on an integral I introduced at the beginning. The real purpose for Simpsons rule and trapezoid rule is for integrals that cannot be evaluated using the fundamental theorem of calculus. So let's say I want to define n for the trapezoid rule so that I could approximate this integral to within 10 to the negative 3rd, 1 over 1,000. So my error bound formula involves the 2nd derivative for 1 over ln of x. I brought that up as ln of x to the negative 1 using the chain rule. It's -1 stuffed to the -2 times the derivative of the inside. And then to get my second derivative, I elected to use the product rule. I did the derivative of this times g plus f, and then times g prime. Turn these into fractions here. This can come down, right, because it's ln of x to the -2, so I can come to the denominator. Then I did a common denominator, ln of x, to get these two fractions the same. And when I simplified it, I got second derivative is 2 plus ln of x, all divided by ln of x cubed times x squared. Now, if I wanted to precisely find the maximum value of the second derivative on the interval from a to b, from 2 to 8, okay, you'd have to think about it. If you want to find the maximum value of something, you need to take the derivative of that, right? This is like a first quarter calculus question. But this second derivative is so ugly, I don't really want to take another derivative of that, right? So we have some little tricks that we can use. And we remember that we're only trying to approximate the error. We don't, any tricks that make our life a little bit easier is fair game if it gives us a reasonable approximation. So one technique has been coined the high-low technique, especially if you have a fraction here. Well, only if you have a fraction, because a fraction has a high part and a low part. And the idea is this: we know the maximum value of a fraction is going to happen when the numerator is as big as possible and the denominator is as small as possible. So if I put the largest number on my interval, 8, into the numerator and the smallest number, 2, into the denominator, this second derivative has a value of 3.06. Now, of course, you're not really allowed normally to plug in one number to the top and a different number into the bottom. But what is true is there's no possible way for this second derivative to be any bigger than if I took the largest number in my interval and put it in the top, and my smallest number for x and put it in the denominator. So it's a reasonable estimation for my maximum value of this second derivative. And if I plug that in, set it less than or equal to 1 over 1,000, do the math, we get n is greater than about 235.7. This was trapezoid rule, so it doesn't have to be even, but we do need to round that up to 236. And just a note here, this high-low technique it's an estimate technique, right? The actual value for n is probably much smaller, but it is using logic to try to come up with a reasonable answer for n. I say that because if this is a book problem and you're looking in the back of the book, they probably didn't use the high-low technique. They probably actually did take the next derivative to find n. And so I'm going to bet the answer in the back of the book is much smaller than that. But as long as you explain your logic in getting this answer, it should be acceptable on an exam. I want to show you one other idea of estimating for this integral. Let's stick with the trapezoid rule. Say I want to estimate the integral from 0 to 1 of sine of x squared to within 10 to the -4th. So the error is bounded by the second derivative. Okay, you got to do a chain rule and then a product rule. I simplified my second derivative to -4x squared sine x squared plus 2 cosine of x squared. And again, if I want to find a precise value for the maximum of this derivative, I would have to take the next derivative and set it equal to 0 and find critical points, which is not going to be fun. So this time, we're going to use some logic to come up with a reasonable estimate. We know that the maximum value for the sine of anything is sine of anything is bounded between -1 and +1, right? Same thing for cosine, -1 and +1. So what is going to make this the maximum? If you think about it, there's already a negative here. So if we want this to be maximum, we would want this part to come out to be -1, because then you'd have -4 times -1, that would be positive. And we want this to come out to be +1, okay? So now, of course, the value of x that makes this -1 and makes this +1 is probably not the same value of x. So just like in the high-low technique, I don't claim that there's a single x value that makes this -1 and this +1 at the same time. But what I do know is this: if this is -1 and this is +1, you can't tell me that you can get a bigger value for your second derivative than what I'm going to get, okay? So on the interval from 0 to 1, I'm going to assign the sine of x squared to be -1, okay? I don't know what x value makes that true, but I know it can't be any, I guess, smaller than that in this case, and cosine of x squared can't be any bigger than 1. Now, as far as that x right there, to make this as big as possible, I would go back to the interval from 0 to 1. I'd want to choose 1 this time. I want to make this as big as possible. And that gives me a maximum value for my second derivative of 6. Okay. Again, just to reiterate, I don't claim that the actual maximum value of my second derivative is 6. It's probably much smaller. But what I do know is it can't be any bigger than 6. I do know that for sure. So that is a reasonable estimate for my second derivative maximum. And if I plug that in, solve for n, I get an n value of, when I round it up to 71. The actual value in the solutions manual might be much less than this, but it is a logical technique that I use to put a bound on my error, and therefore come up with the, if I use 71 trapezoids, it is guaranteed my error will be less than 10 to the -4th. Let's just put it like that. Okay,